So here we're looking at a definite integral, and anytime you see a definite integral, once you've defined what an improper integral is, what you're always going to have to consider is the possibility of this integrand, this function right here, being undefined at or between the limits of integration. So if you think about this denominator right here, if I put a 4 in place of x, 4 minus 4 is 0, I'd have division by 0 when x is 4. 4 is my limit of integration at the lower end. So this is definitely an improper integral. And what that basically means is that the fundamental theorem of calculus, that the part of it that allows us to evaluate a definite integral, it doesn't work directly for us. We're going to have to kind of trick that theorem into working. So what we're going to do is we're going to switch this lower limit of integration from a 4 to some other value. I'm just going to pick the value of a. I'm going to still keep the upper limit of integration okay. The only thing that I have an issue with is the lower limit of integration being a 4. So I'm switching the lower limit of integration. The integrand is going to stay the same for the time being. And what I'm going to have to do out here is I'm going to have to give myself a way to let my lower limit of integration approach 4. I can't let it equal 4. If I equal 4, then I have division by 0, and that's a no-go. So I can do a limit as x approaches 4, but I can only approach 4 from one side. This interval from 4 to 10 is okay. The other side of 4 is not okay. I can't put a 3.5 into this function. I'd do the square root of a negative then. Those values wouldn't be in the domain of this function. So I am only allowed to approach 4 from the bigger side, or else I'm going to have an issue because of the nature of this integrand right here. So now we're ready to go ahead and try to do this integral. So once you make this switch, you're now in a situation where the fundamental theorem of calculus can be used because we're not letting this lower limit of integration equal 4, we're letting it approach 4 from the bigger side, and you can definitely have x values go here that are slightly bigger than 4. So now we're going to be just carrying this limit with us throughout our work here. So we're going to eventually have to do a limit. Whoops, and I have the wrong value here. I'm not supposed to let x approach 4. Let me backtrack here. My lower limit of integration is supposed to be what approaches 4. That's my fault. Right, this is what I want to let approach 4, this lower limit of integration. So I just wanted to kind of clean that up there. Sorry about that. I can still only approach 4 from the bigger side with that lower limit of integration. Now if you think about how you're going to do this integral right here, you have a square root that can be rewritten as a 1/2 power. That 1/2 power is going to be in the denominator. So what you'd probably do with this integral is you'd probably move that quantity that's the 1/2 power across the fraction bar into the numerator, change the sign on the exponent, and now you're going to be in a situation where you'll have an easier time evaluating for the antiderivative of what's here. The issue is you still have an inner function sitting here. And anytime you have an inner function in an integral you're trying to carry out, you're going to try to let u equal that inner function. And in this case, if you think through the substitution steps, you should realize that this substitution is going to clearly work because our derivative, du dx, when we're trying to figure out what we're going to have to replace dx with, du dx is going to equal 1. So du is a direct replacement for dx. Multiply both sides by dx, and you realize that du equals dx. So limits of integration are still a and 10 there. I'm still trying to do a limit as a approaches 4 from the bigger side. I'm not going to do that till my very last step. I just can't forget about that being something that's essential to do here. I'm going to pull the constant 2 out in front of the integral as well at this point. And then in place of this x minus 4, I'm allowed to put u, right? U is equal to x minus 4. So we're going to have u to the negative 1/2 du within the integral. Now the only other change that you might want to make here is you might want to change your limits of integration. Notationally speaking, you probably should change these limits from values of x. Right back here, the a and the 10 are assumed to be values of x because that's the differential within this integral. And now that we have a new differential, we would probably want these limits of integration to be values of this variable, u. So if u is equal to x minus 4, what is u when x is equal to 10? Well, when x is equal to 10, u is going to be equal to 6. So our upper limit of integration is going to be a 6. And then our lower limit of integration, what is u when a is equal to, when x is equal to a? Well, u is going to be a minus 4, so we kind of get an ugly lower limit of integration, but that's okay. We'll deal with that when the time comes. Now we're ready to go ahead and do our antiderivatives. So can't forget about this limit. Have to carry it through within our work here. We're letting a approach 4 from the bigger side. 2's still there. What's the antiderivative of u to the negative 1/2? Well, if you add 1/2 to that, you get 1/2. If you divide by 1/2, that's the same as multiplying by 2. So here's the antiderivative of u to the negative 1/2. I need to evaluate this antiderivative at u equals a minus 4 and at u equals 6, and I'm going to take a difference at that point. So the last thing I'm going to do here, I'm just going to multiply this 2 by this 2. Be a little easier, save a little bit of space here if I do that. So 2 times 2 would obviously give me 4, so I'm going to have 4, and then in place of this u I'm going to put 6, so I'm going to have 4 times 6 to the 1/2 power minus 4 times, I'm putting a minus 4 in place of u, so a minus 4 to the 1/2 power. So now if we're letting a approach 4 from the bigger side, we're finally ready to try and evaluate this limit. So putting 4 here is dangerous to do because this is really a square root, right? A 1/2 power indicates a square root, and we can't approach 4 from both sides. We're going to get imaginary values on one side of 4, but the bigger side of 4 is okay, right? Values slightly bigger than 4 are going to give us, when we take a difference between 4.1 and 4, values slightly bigger than 0 that we're trying to raise to the 1/2 power or trying to take the square root of. So this is going to be okay. We're going to get 4 square root of 6, so I'm just kind of reverting back to root notation rather than fractional power. And this other piece here is going to be 4 square root of 0. We just had to confirm that we could put values slightly bigger than 4 in place of this a. We did that 30 seconds ago. And what we end up with for the value of this improper integral is 4 square root of 6. So this improper integral converges, and its value is 4 square root of 6.